Good morning. So now and then you encounter an idea that's so beautiful, so right, that you wonder how no one managed to think of it before. And for me, Robbie Findler's treatment of contracts for higher order functions is that kind of idea. Of course, no one did, and Professor Findler worked it out while doing his PhD at Rice University, and then he presented it here at ICFP 12 years ago. He subsequently moved on to the University of Chicago, where he was instrumental in developing something that I think is really cool, and if you haven't checked it out, you should, PLT-REDX, which is a domain-specific language for semantics engineering. He's now an associate professor at Northwestern University, where he's been working on parallel and distributed programming in Racket, and he continues to work on contracts, deepening our understanding of Blame and adapting them to new settings, new language features, and new applications. If you are unfamiliar with his work, then this should be a treat. And if you are familiar with his work, then you're probably looking forward to what he has in store for us. So please join me in welcoming Robert Bruce Findler.
Thank you for that very kind introduction. And also, I'm very grateful to be given the opportunity to stand here in front of you and get your attention for an hour. ICFP has always been a home away from home for me, and so this is really an honor from my perspective to be able to be here and talk to you. So thank you for that. Okay, so there's far too much, I think, to say about behavioral software contracts and can possibly fit in an hour. So if you look in your proceedings, you'll see where the abstract would normally be for the keynote talk is an annotated bibliography of the work on software contracts, specifically focusing on higher order contracts and Blame. And so I'm going to treat that as a license to basically not talk about a lot of stuff and to pick out a few things that I think are interesting and that make for a nice talk and just show you those. So if any of the stuff piques your interest, I encourage you to go have a look there for the whole story. A lot more to say that you can find leads from that spot. Okay, so in that spirit, I want to start with a pragmatic point, which is that contracts are infectious. So I'll use this initial section of the talk to explain what I mean by that, and then also to just kind of get you in the feel for contracts and what it's like to program with contracts in Racket. Okay, so here's some code, and I want you to imagine that you wrote this code. This is your code, okay? Your boss assigned it to you, and you've produced it. He told you, you have to make a function that accepts a pict, which is a functional picture data type, and an XY coordinates, and then to return Boolean indicating whether or not that point is in that pict. Okay? So this is what you produced, and let me walk you through what you've done. So here's a call into that function, and we're in a call by value language. So the first thing we do is we're going to evaluate the arguments. So that's our cloud of size 100, 100, and there's the coordinates at 0, 0. And then the next thing that happens is we'll enter the module. And now that we've entered the module, we can do substitution into the body of the function. And we're now at this call to pin under. And what pin under does is it takes its last argument and sticks it at the coordinates, in this case 0, 0, relative to its first argument, and creates a new picture. So, disk 1 actually returns a circle of size 1 pixel, but I've just made it a big red ball so you can see it in the talk here. Okay, and then now we have a value for the p dot variable, so we can substitute that through. And then picked arrow ARGB pixels constructs a bitmap corresponding to what it looks like to draw that picture, where there are 4 bytes per pixel in the original. The alpha, the red, the green, and the blue. And so this is the prefix of those in this case. And these are not equal to each other. And so therefore, the coordinate 0, 0 is not in the pict, in that cloud pict. Right? So it returns false in this case. Okay, so if we were to call this function with cloud 0, 0 and 50, 50, well, the same exact series of steps happen until we get to this point. And now what pin under will do is it'll put that red dot kind of at the coordinates 50, 50, which happens to be underneath the point where the drawing happens. So we just get the same pict. and then do the substitution, and call picked arrow ARGB pixels again, and now this time we get identical byte arrays. So that means that the point 50/50 is in the pix. Okay. Okay, so that's good. And you put this into your code base, and you're off and running, and about a week later, somebody writes a program that uses your library to do stuff, and effectively does that in the context of some larger program where your library is being used. And so, of course, what happens is the system gets angry at you, and this is the contract violation. And I should say at this point that all the code that you see in this talk is actually running code. That this is a presentation that's written in Racket, and so all the code is actually run before it's put on the slide. And anything that's the output, which we'll see plenty of output of code here today, it's all the result of running it and put in the slide. So there's nowhere in the source text of my presentation that has this red stuff. Okay, it just ran it and then took the output and put it in the slide. So okay, so there's a lot of information there which would be useful to you if you were actually trying to track down how this happened. But for the talk, what I want to do is just focus your attention on that second to last line down there. And that says that it's your fault for this error that's happened. Because that was the name of the module that we entered, as you may recall at the beginning. The point in module is the one that contains the code that you wrote, that your boss asked you to write. Okay, so why did that happen? Well, when you pass false false in the same way that we passed 0 0 in, we get to this same spot in the evaluation, just as before. And pin under has a contract on it. And pin under's contract says that my second and third arguments must be real numbers, and false is not a real number. So okay, that's why the contract violation happened. Your code allowed us to get to this position. Why? Because your code didn't have a contract on it. Okay, so I'm sure the audience right now, all of you are thinking to yourself, types? What are you doing here? Okay. And of course, that's a fine place to start when you're thinking about contracts. Okay, so let's start there. And so this is the contract version of the type that you might give to that function. It says that it accepts 3 arguments, a picked and 2 reals, and returns a boolean. Okay, and the way that you put that contract in is you put it there. I colored it red in the code so you can pick it out. And before we just said provide point in, and now what we're saying is provide with a contract, point in, and then that's the contract. Okay. And now if we make this same call, well, what's going to happen, we're still going to evaluate the arguments to the function, so we'll still actually compute this cloud. But then, at this point, we won't be allowed to enter the module anymore because the contract is guarding access to this module and only lets you enter the module if you satisfy the contract. Okay, so this is the error message that we get now. It says that we expected a real, we got false in the second argument of that function. And now we're blaming the top level. And the top level is just Racket speak for code that exists outside of a contract, which is how I happen to set up this particular call for the talk here. Okay, good. So contracts are infectious, and they're infectious basically because of that series of steps that I just talked you through. Imagine that was your code, and so somehow it got blamed. And now you take this kind of very negative feeling of blame and turn it into a positive by making it be somebody else's problem, roughly. Okay? And so this is a graph over time showing you the number of contracts in the Racket code base over the last 3 years, basically. So roughly all the time since we started, shortly after we started using Git, and shortly right after we stopped figuring out that we shouldn't do merge branches. Okay. So I didn't go any further back than that. And so, we have time along the x-axis here, and then the number of contracts. And you can see mostly it's this kind of gradual increase. Okay. There's a few spots it's not, so here's one. This was when Ryan Culpepper added the database library to Racket. And Ryan's a good citizen, and he decided that he would write contracts right from the start in the library. And so that gives you maybe a sense of scale of this graph. That's how tall one library's worth of contracts is. Okay. This one's an interesting point. It goes up and right back down again. And that's because Neil Taranto implemented a ray tracer. And it uses lots of floating point matrix operations, and he wanted to use the unsafe operations to do that to get some speed. And so he put contracts in to try to avoid having seg faults when people would pass in bad inputs to his ray tracer. And then shortly after he did that, he realized that actually using typed racket would be the way to go. And so the contracts, he took them all right back out again, and in favor of making the things be typed. And that's totally the right call in this case. Okay, and if it's not obvious, this is a histogram of the delta of the contracts in the commits. So it's showing you that most of the commits that change contracts at all add one contract. That's that big spike in the middle. I left out the spike that corresponds to a change of 0. So you can see like a little sliver of white in there. That's just because I left out 0 because it would swamp the graph. So most of the time we're getting one contract added when contracts change in a commit, and then a little bit less frequently we get 2 added, and most of the time there's a small number of changes. So all this is to say not proof that contracts are infectious, but it's suggestive that that's probably what's going on here. Okay. All right, so I said earlier that types are a good place to start when you're thinking about contracts, and so let's see if we can take the next step and go a little further than what you might be able to commonly say in a type system. Okay, so here's our same code that we had before, our point-in function with its contract type style contract, and a call that says we're going to pass in -50 and -75 as the x and y coordinates. So that passes the contract because those are both real numbers. And so we get to the same spot that we've been to now 3 times in the talk, or 4 times or whatever. And what does pin under do when it's given negative numbers? Well, it's fine with that. It just puts it at the coordinate -50, -75 relative to the upper left corner of the pick that's given. Right? And one thing I didn't mention about pin under before is that it doesn't change the bounding box of a picked. So when you use pin under, you can get a picked back that draws outside of this bounding box. And that's not wrong. Really, the word bounding box is what's wrong. Really, you should think of each picked coming with like a local coordinate system, and it can be very useful to draw outside of, beyond 0, 0, or down to the right of that. And so this talk is using picks all over the place, and I use this in order to make these animations smooth and things like that. Okay, so anyway, pin under, it's just sticking it outside. Okay, and then picked arrow ARGB pixels, of course, it can't take the entire R2 plane when it's building its bitmap. It has to be restricted to some finite thing, and so it's defined to work only on the bounding box. So it's only going to consider the pixels that are drawn inside the bounding box of the given picked, of which this red dot is not. So what we get are the exact 2 same byte arrays. So this will be true, and so now what the function is saying is that -50, -75 is in the picked, okay, which is wrong. Okay, so if this were a talk about bounding boxes and coordinates and picks and things like that, we might try to fix this function. But any fix, then there's multiple different ways you could fix this, but any fix I think is going to rely on this function, at least as some kind of a private helper function. And this is also a talk about contracts, so let's see if we can't come up with a contract that actually captures the places where this function works correctly. Okay. So here's the contract that we had, and let me just pull apart the pieces there for you for a minute. It's a arrow that hyphen greater than is a function, effectively a function. And what it does is it evaluates its arguments and then constructs a contract that works on functions. And then also, so picked, real, and Boolean though, those are predicate functions. And so contracts just take predicate functions and lift them into contracts when they're used like this. So we're just taking the picked predicate from the picked library and the real number predicate and the Boolean predicate and putting them all together to make this function contract. So since those are just predicates, we can certainly make up a predicate that would disallow the coordinates -50, -75 by using a different combinator from the contract library, or just writing out a predicate that says positive real numbers only, or non-negative real numbers only. And so that's the way that you would write this in the contract library's combinators. It's the /C means I'm a contract, and greater than equal is the contract that accepts numbers that are greater than 0 in this case. Okay, and that works fine for the example we had, but you can also have coordinates that are wrong, that are too far down or too far to the right, not just too far up and left. And what are you going to do about those? The actual size, the actual bad values will depend on what the picked is, right? So that's a clue, depend. Okay, so we need to have a dependent contract to express that. So I'll change this now. So bear with me, a little syntax for you. So let me make a little space. And this is the exact same contract, but written using the dependent contract combinators notation now. So basically all I've done is I've given names to the arguments and put a few more parentheses in. So it's saying that we're getting 3 arguments still, P, and now we have names for them, P, X, and Y. In addition, but there's still no dependency, and this is still the exact same contract. Okay. In order to actually express the dependency, you have to declare which arguments depend on which other arguments. Okay, so I need a little more space to do that, and this is the way that you write that. So it's just saying that X depends on the value of P. And so now we're set up to be able to actually write the contract we want to write, although I need yet a little more space for that. And here it is. So this is saying that X should be a real number whose range is between 0 and P-W of P is a shorthand for writing out extract the width from P. So it should be a real number between 0 and the width of P. Okay, so for those of you who've maybe worked with dependent type systems before, you might think, okay, and real programming languages, are we going to be, okay, so, but in the world of contracts, there's no problem for checking contracts like this because you actually have the arguments before you're going to do any checking of the arguments. So you can just substitute in the actual pick that you get here and then you're going to find out that you should have a real number and you're going to have actual values for knowing what that real number's range should be. So here's what happens with this contract now on our point-in function. It says that the point-in function has a contract violation. I expected a real number between 0 and 100. And that 100 is there because we evaluated the expression that was behind X in the contract. Okay. All right. The interaction, though, between dependency and ordinary programming languages that have state and effects is interesting. So there's something more to be said here about this, but in order to explain it clearly, I want to switch to a different example. So this is another function from the PICT library called DC. And it's really the kind of low-level bridge between the functional combinators for building pictures and the operating system provided imperative interface that actually does drawing. So you give it a function. That function should have some side effects of doing some drawing, and you give it bounding box information. So DC's first argument there is a function that will then use imperative commands on that DC that's being passed to the lambda to do actual drawing. And then the next 2 arguments are the bounding box. So we're constructing a pict whose size is 200 by 120 thanks to the last 2 arguments to DC. And then the function there is going to say draw an ellipse. And so that's why we see a black ellipse here, because that's the default color that we get in the DC. Okay, and so colorize is a function that takes a pict and then turns it a particular color, so blue in this case. And the way it works is that every function can be turned into, or every pict you can extract the procedure that does the drawing for it. And so what colorize does is it extracts that function, then wraps it with something that mutates the state of the drawing context. So it'll wrap this procedure that's being passed to DC in the resulting pict by something that changes the state of the drawing context to now draw blue, but then calls the function which draws the ellipse, and then changes the state back to draw whatever color it was being drawn before. So that's why we see that we get a blue ellipse now instead of the black ellipse. Okay, so make a little more space here inside this function, and then I'll grab and restore the brush state, which is where the color is saved. And now I'm going to change it to red. So this is not anymore a function that draws an ellipse, it's a function that draws a red ellipse. And so if I color this one, nothing changes because of the way the wrapping in the set of the state happens. It's effectively ignored by this function setting the state directly. Okay, so that's the DC function in the PICT library. And it has this invariant having to do with the state of the DC, namely that you set and restore the state properly. So here is a use that doesn't do that. Okay, so this light background color square in the definition of EPS up there is the same code from the very first use of the DC function that I showed you a moment ago. And so it's just drawing a natural color ellipse. And then this guy, the define red, this is a broken use of the DC function. So I have to call unsafe:DC here, which means I hack the PICT library to extract the version of the function that doesn't have a contract on it, because the contract would signal an error and would crash the talk right now if I used that. But what it's doing is it sets the state in such a way that things are going to be drawn red, but then doesn't set the state back So it doesn't properly restore the state. So you see there's 2 calls there and 1/3. Okay, and then we'll just put them all together, and that's what's making the picture over there on the right-hand side of the slide. So VC append just combines things vertically. That 20 means put a gap of 20 pixels in between them. And we have the natural colored ellipse followed by the red one, followed by the natural colored one. But you see it's drawn as black, red, red. And this should really be drawn as black, red, black. Okay, so that's already telling you something about the behavior of the VC append function. In particular, it draws what order it's drawing them in. And so you can see the state pollution is affecting that last one. Okay, so that's the contract. We want to get a contract that would signal a contract violation and blame the use of the DC in the definition of red there, that it's not correctly playing along with the protocol for managing the state in the DC. All right, so here's the kind of type-based contract using that notation we've seen. So F is the function that's we want to make sure that it behaves properly. So one natural thing to think about doing here is to just grab the state right before you call F, and then grab the state right after you call F and check to make sure that they're the same. That's a bad idea because the primary reason is that the checking happens too late. So this talk is all full of pics everywhere, so in analogy to the talk, that would be getting a contract violation like on the next slide. And what I really want to do is I want to get a contract violation when I call the DC function, when I build the talk. So when I fired it up, I don't know, about an hour ago, that would have been a more useful time for me to get the contract violation if there was one. Okay, and then it's also more expensive because the function F gets called a whole lot more than the DC function gets called. And so we'd like to be able to do the checking earlier. Okay. So a little more notation for you. We make a space. And in the arrow I combinator, you can specify a precondition. And so you put this optional keyword #pre. You declare what variables your precondition depends on, F in this case. And then we're defining this, or we're using this function restore state after call. So that function accepts F and should return a Boolean indicating whether or not F restores the state after the call. And so it does what you think it does. It creates a DC, it randomizes the state in the DC, it grabs the current value of the state, calls F with that temporary DC it's created at the point 0, 0, and then checks to see whether the function obeyed, whether the function restored the state properly after it was called. So this contract is not some notion of total correctness here, right? Because it's only calling F once, and it's only calling it at 0, 0. But in general, these functions don't modify the state in a way that depends on where it's being drawn. They always modify the state, they never modify the state. And so, although it's possible to write a function that would modify the state the third time it was called, that's also something that just doesn't really happen in practice when you're using these contract combinators, or when you're using these picked combinators. And so this contract is actually very useful because about an hour after I committed it to our code base, I got an email from the integration build server telling me about a bug that was 3 years old and trivial to fix now because of one of the uses of this DC that didn't properly restore the state. Okay, so all that's to say, this is I don't know. I mean, this is a little bit of a strange contract, okay, and it raises some interesting semantics questions. Okay, so let's investigate those. Okay. And okay, the first thing I have to say here is to those who maybe have studied the semantics of contracts a little bit, I should apologize because this for a long time I thought was the right way to think about contracts. And if you're not familiar with the idea of contracts with projections, okay, you can just tune out for a minute. But this is a bad idea. So I used to have the thought that a contract system design was good if all the combinators produced always projections. That example we just saw is a good contract in a pragmatic sense, a useful contract, and it would be ruled out by the contracts as projections notion. Okay, and so that means this is wrong. Okay, so all right. Anyway, the right way to think about contracts is to think about boundaries, and I will explain this part to you. But first, I want to say that this is work that Christos did. So Christos worked out a whole meta theory around contracts and boundaries in a way that the meta theory actually is a very powerful design tool for deciding how to add contracts to new features to a language that you're working on. And so I'll show you one instance of that in the case of dependent functions. Okay, so here's the standard call by value, simply typed Lambda calculus. Let me know if you're spotting errors. So I'll just, let me zoom in a little bit here to show you the contract parts, which are the only thing interesting, the only thing you haven't seen before, probably. So this is the typing rule for typing base contracts. Okay, so we have contracts tau is the type for values that are contracts that operate on values of type tau. Okay? And this is the way that we're going to get contracts on things like booleans and integers. If you have a predicate that operates on a base type, then that predicate is also a contract on that same base type. If you have two contracts that operate on tau1 and tau2, then you can put them together to make a contract that operates on the functions between tau1 and tau2 by using arrow. And then the third piece that you need is a way to actually put a contract into a program. And this is how you do that. You use mon. So mon means I'm monitoring a contract. It has two labels, A and B, and what those labels signify are the contract is being protected, the contract is protecting the boundary between A and B. So we have a value that's supposed to live up to the contract that is E1. The value will be the result of evaluating E2. And that value is going from A to B. Okay, that's what the mon construct says. So if you're thinking about the module system and contracts and modules, then you would imagine that there's some kind of compilation that turns modules into maybe just ordinary variable references with mons wrapped around them where the contracts were. Okay. And then here's the object of our study, the dependent contract combinator. You give a contract for the domain. You give a function that will compute contracts for the range when it gets a particular element of the domain. So you don't just get to, you actually get to know what the argument was before you decide what the contract on the result is. And that's the dependency. So it's a simplified form of dependency compared to what we've seen before, but enough to kind of illustrate the issues here. And that arrow I has a little C on it, and that's kind of the punchline of this section. Okay, so I'll return to why there's a C there. But this is the contract. So it gives you back a contract on the function space between tau1 and tau2, enabling you to make a dependent, use contracts independent there. Okay. All right, so now I'm going to show you a series of pictures from which we will learn the rules for that describe what the behavior of mon is given various contracts. And the pictures will always have this shape. We'll have the good side over there on the left in black, that's us, okay? And then we'll have this blue line, the thin blue line that protects us from the scary other side. And that thin blue line will come with the contract. So in this case, the contract is saying that the values that are allowed to pass should be less than 3. So here's a value. It's off in the scary side, and someone's trying to send it into our code. Well, it enters the contract, then some computation happens to determine whether it's a good value or not. So in this case, we're going to compare it to 3, and it is a good value. So we color it in as appropriate to be allowed to the other side, to our side, and then we let it, and then the boundary will let it pass since it passed the contract. Okay, and so here's what happens when a value is not suitable for the contract. It's still allowed to enter, just as before, but now this computation is going to tell us it's a bad value, so the contract boundary will not open on the other side, and the value will not be released, and instead what happens is the program is aborted. Okay. So all that's to say, this is the rule. This is the equation that should hold for the behavior of mon given a value and a predicate contract. It's just equivalent to doing a conditional test. Okay. So if the predicate holds for the value, then the mon is equivalent to the value. If the predicate does not hold for the value, then blame A, and that's another piece of the calculus, and it just aborts the program and says A's fault. And it should say A's fault in this case because this is a monitor that's protecting values flowing from A to B, and so A produced this bad value, so we blame A. Okay. Functions. So we have a function contract saying that we want to take in numbers less than 3 and return numbers less than 3. And there's our function there, which is coming from the scary side. It enters the boundary just as before, and it's checked to see whether or not it is a function and whether or not it's a function of arity 1 in this case. So in Racket, those checks have to happen. In the calculus, the type system is going to guarantee that those particular things hold. Okay. And then since that's fine, we're going to color the contract in, and we're going to allow it to go to the plug the function in, and then we're going to allow it to go to the other side. But there are residual boundaries that are left behind in the case of a function that are going to protect the inputs and outputs of the function. Okay. So here's the way that's written in the calculus and the rules. We say that if we have a monitor on a function from domain to range, well then that's equivalent to this other function which checks that the values that come in obey the domain and the values that come out obey the range. And you see the labels are swapped in the case that there's an argument, because if you have a function that's flowing from me to you, then you call the function, you're sending a value back to me again. The flow of values is reversed, and that's why we need to reverse the labels. So if the function goes from A to B, then the argument is coming from B back to A, but the result is again going from A to B. Okay. Usual contravariance relationships showing up here in the calculus for contracts. All right. Okay, so there we have the basic rules for the function contracts and base contracts. And let's look at dependency now. So I'll make a little space, and let's turn this into a use of the dependent function contract combinator. So this rule is, as written, bogus, because on the left side of the rule we see drange, and on the right side of the rule we don't. We see range instead. So let me make a little space. Okay, and we can bind range by just calling drange with x. So that's how we resolve the dependency. Fundamentally, we want to get the range contract by passing x into this dependent range function, right? If you remember the types for arrow I. And this is the rule that we had in that paper in 2002. And this rule is wrong. Okay. So, because the dependent range should really be allowed to know that the input to the function satisfies the contract for domain. Okay, so I'll make a little space, and no problem, I can just stick the same monitor there. Okay. And this is the rule that Michael Greenberg and others worked on, and this is a very nice paper, this one I'm pointing to. It, among other things, illustrates very clearly that this rule is better than the previous rule. It says very clearly that rule is wrong, and this rule is more right. Okay. This rule is not yet completely right, however. Okay, and so let me show you why. So here's our function. It's in the contract boundary, and I said that we're just going to do an arbitrary computation to determine whether or not the function is suitable to be passed out. And well, arbitrary computations can do things like call functions. There's a function. They can do things like get the number 4 and pass it into the function. Whose fault is it now, right? 4 is clearly not supposed to be allowed to be passed into this function. This is supposed to be a function that takes numbers less than 3 as arguments, but here, the contract boundary itself, since it can do whatever computations it wants, is doing something wrong. And this could have happened, right? With our example where I called f DC00 before, there was a contract on f. F was supposed to get real numbers. Okay, so 0 happened to be a real number, so we dodged a bullet there, but it might not have been. There might have been a bug in the specification itself. And so the contract language and the contract calculus have to be able to cope with this. So where is that value 4 coming from, and where is it going? That's what we need to answer to be able to give the correct rule for the dependent contract combinator. And so here's the rule that I had just a moment ago, and let me change it a little bit, and there now we see the label on the arrow I. So the arrow I comes from a place. It's got code in it. That code was written in some module somewhere. So, okay, we put a name that indicates the provenance of that arrow I's implementation. And that's where X is flowing in the first case. X is coming from B in both cases. It's both being supplied as an input to this function. So that B is the correct first label on the mon. But in the first use of mon there on the right-hand side, it's flowing into the contract, which might turn out to be the same as either A or B, but in general, it could be something different. Okay. And returning back to Christos's meta theory. Christos' meta theory forces us to do this. Okay. The theorems that he tells you should prove about a good contract system don't hold unless you use this rule. Okay, and they do when you use this rule. Okay, all right. So last section, I want to talk a little bit about applications of contracts. Okay, so I've shown this picture to you a number of times now, and we thought about it as breaking down one program into 2 pieces where a contract is controlling the behavior between the 2 pieces. And when you're programming, if you want to be successful, you might imagine that you don't have the other piece, right? You're going to sell your code, right? So I use the word component here, perhaps as a reference to the software component marketplace. And so you might not have component B. Can contracts do something for you in this case? Well, what if we were to just say, put something random on the other side? So arbitrary stuff. Okay, I'm going to make up something random. I can make random things up. I'm going to put them on the other side. Well, what can happen when I do this? Well, I'll probably get a contract violation. And that contract violation will probably blame randomness. Okay? But okay, that's fine. I'll just ignore that one and I'll try again. And again, and again. And then eventually, I might get a contract violation that blames my component. Okay? And I found a bug when I did that. So Racket's contract system does this. This is the implementation of a binary heap in the usual way with a vector where you use indices into the vector and arithmetic to determine where the actual tree elements are. Okay? So let me zoom in on the contracts. So we've got 3 functions. And this is just a simplification of the version of the binary heap from the standard library in Racket, where we've got a new heap that creates a heap. We've got insert that inserts an integer into the heap, and delete that removes it. And you see I'm using the post condition here to check to make sure that the heap is actually valid, where valid heap means walk over the vector and make sure that it obeys the heap invariant. Okay? So as far as I know, this code is correct. But there's some less thans in it. So let's make them greater thans and then try and see if the Racket contract system can catch that. And so this is called mutation testing, a particular kind of mutation testing. So there's the first one, that red dot there in the bottom left. Okay? And here is how you ask the Racket contract system to set up that blue boundary and then make some randomness on the other side of it. You use the contract exercise function. So what this is saying is make that picture. On the good black side, we'll put new heap, insert, and delete. And on the white side, put randomness and use the contracts that are on new heap, insert, and delete as the blue line. Okay. So, all right. So let's do that. Okay. So, yeah. Okay. All right. That's all right. All right. There's another less than in the program. Let's try that one. Okay. Good. So good. Okay. We found a contract violation. We needed a binary heap only of size 2 that happened to have that funny number in it and some other stuff that I cut off because it would have gone off the edge of the slide. And I should remind you at this point that I don't actually know what's going to be on the slides in the next couple slides because it really does run it, okay? And so I don't know exactly what's going to appear on the next slides. So, okay, fingers crossed. There's 5 more less thans, so let's turn them into, okay. Okay, good. It found all of them. So we need like the top 2, it needed a heap of size 2, a heap of size 4, size 3. It needs small heaps, in fact. These are actually easy violations to catch. I've never been able to catch this one. And so after a bunch of tries, I took a look at the code and thought about it. And this is the test to see if the vector you have is big enough. And if it's not big enough, it'll double the size of it. And so when you reverse the sense of that comparison, it will say when it is big enough, double the size of it. So it's not actually violating the contract to change that less than to a greater than. So again, contracts are not total specifications. In this case, the partiality has to do with the size of this internal vector. Maybe it's a relationship to the size of the number of actual values in the heap or something like that. Okay. All right, so that's one application. How does this work? Well, so let's go slightly more abstract. Here is a contract that is on a function that takes an A to B function and gives you back a C to D function. And it's the contract's job, the contract system's job will then be to make up B's and C's. It's easy to make up a function, just lambda, okay? So the interesting thing is making up the parts that are not the lambdas. So we have to make up a B to be able to make up this function, and we have to be able to make up a C to be able to call the partial function that we get back. And there's basically 2 ways you can do that. One is there's a bunch of built-in things the contract system knows about. It knows how to make up real numbers. It knows how to make up Booleans, stuff like that. It knows how to make up lists of things, given it knows how to make up the things inside the lists. But that's not enough. You might not be able to make up all the things, but that's okay. The function you're testing might actually give you values you need to break its own contracts. Okay? In fact, it generally does, it always does that, in fact. And so you get to use A and D. So the contract system has a notion of contract stronger. It has a notion of whether one contract is stronger than another. So if the contract A turns out to be stronger than the contract B, then we know whenever we have an A, we can use it as a B, or you can use it as a C. So the contract system just stashes aside any values that it's being given from the program under test and then uses them later. And returning to the contracts on the heap implementation, that's critical because this heap C is not something that the contract system knows about. It's in fact defined privately as part of the library here. And so, but happily, there's one where it appears in a positive position, so the contract system knows to call new heap before trying to call insert and delete, which, okay, is something that you'd expect it to be able to know. All right. Okay, 3 more applications that I won't explain in quite the same level of detail. Probably the one that you were thinking of is gradual typing is probably the most this is probably the most active application of contracts right now. There's a lot of work going on with gradual typing. And the idea there is that on one side of the boundary, we have a language with one type system, maybe no type system. And on the other side of the boundary, we have a language with a more interesting type system. So like racket and typed racket, say. And it's important that the invariants that the type system establishes are not subverted by the untyped side, which it's going to interoperate with. And so what you can do is you can construct contracts that correspond to types and put those in that blue line, and that will guarantee that the untyped side doesn't do anything that would cause the assumptions made by the compiler, say, on the type side to go wrong. And instead what you'll get is an error at runtime. Okay, and I'm particularly pointing out typed racket here, not because I'm a homer, but because this is the implementation of these ideas this is the only real implementation of these ideas. There are other younger implementations that will probably catch up to typed racket at some point. But if you've heard about gradual typing and you want to give it a try to see what it's like to program in a world with gradual typing, typed racket is the thing to try. Okay. Another one that I think is particularly cool, and you can hear more about in about, I think, 40 minutes from now, is how static analysis plays with contracts. So there's this. So you put racket on one side, and now you want to prove your racket program obeys the contracts that are in that blue line. And what Phil and Dave Van Horn and Sam have done is come up with this technical device called Havoc, which you put into your static analysis. And what Havoc does is sort of everything that's allowed to do non-deterministically, except what the contract system forbids. And so if you can prove that when you combine your program with Havoc, it doesn't signal any contract violations, then you know there is no program you could combine with your program that would cause it to signal contract violations. And the final application is, using the word application is unfair to this work, actually. But it does share kind of some core ideas with contract systems as one of the technical devices that this work uses. So the idea is that you have, on one side of the boundary, you have an invariant-rich language, a language where the programmer knows a whole lot about the programs just because of the syntactic. They're very limited, the kinds of syntactic constructions you can make in that programming language, and therefore there's lots of invariants about how programs behave. So the simply typed land calculus is kind of a classic example of something where there's lots of invariants and you know a lot about how the programs are going to behave. And then maybe on the other side, you want to interoperate with a programming language that doesn't. It has all kinds of crazy stuff like continuations and assignments and things like that. And so boundaries in this world become a technical device to help you control and understand where the invariants hold and where they don't hold, and let you set up the formalisms you need to be able to prove, in the case of what Amal's work is doing, that your compiler, when it produces binaries from these two different programming languages, that they can interoperate in a safe way, such that the invariants that the STLC programmer was relying on are not corrupted somehow by this crazy world that it's interoperating with. Okay, so let me recap. Okay, these are the points I would like you to try to take away. So first off, contracts. I've had many conversations where it comes to light about halfway through the conversation about contracts that my conversational partner has sort of always thought about contracts as if they were sort of a crappy type system. And so I hope that maybe I've convinced you that's not the case. But maybe if you need a little more convincing, I want to point to Jesse's work on affine contracts. These are contracts that fundamentally use assignment in the contract combinators themselves. Okay, so it's kind of an interesting thought that you need mutation in the combinator, its implementation itself, to be able to express the contracts that you want to say. Okay. Contracts infect code bases. You just get them started, and this negative feeling of blame is going to cause more and more and more of them to appear throughout the code base. My apologies again. And boundaries are a very important concept that you should perhaps think about when you think about interoperating systems or contracts, or there's lots of different things where boundaries play important roles. And I want to leave you with one positive thought for the world going forward. This community has, and I'll use a pejorative here, locked up inside it a lot of knowledge about how to establish that specifications hold. Contract system infectiousness gives us an opportunity to unlock that knowledge and to share it with the world in a very positive way. If we can just get contracts kind of seeded into a few, popular programming languages, or a few popular libraries in programming languages, then they're going to grow throughout code bases all over the world. And then people will come to us and they will say, I really wish I knew this was true, for sure. Okay, so go get it. Thank you.
Thanks. So we have questions? Or, please.
I was quite familiar with using constrained random simulation to prove whether your assertions or your contracts with CTS thing are correct or not. But quite early on, you're using randomization of the graphics context as a way of demonstrating that whether the thing was okay or not. And I think that would kind of break any formal tool using a random number there. Wouldn't it be better to use, for example, not a number as the invalid context rather than randomize?
So I used randomize because in the actual code I used randomize because it could easily be the case that you're mutating the state in such a way that you're setting it to the defaults and the contract won't check it. And if you randomize it, then you're unlikely to have that happen twice. So that was sort of a pragmatic choice. And I can understand how using a different form of specification would certainly lead to be more amenable to proof. So that'd be great. Yeah.
So contracts for you are mostly checked at runtime, and they're infectious in your library. So I'm just interested in your experience about whether as a library author, you experience a tension between the runtime overhead of checking the contract. You'd like to do valid heap and walk over the entire heap every time you insert an item. And whether you experience a tension between the coverage of the contracts and the cost of checking them at runtime. And whether then programmers ask you, couldn't you give me a switch to let me switch this off, please? And the whole bounce checking thing. So just tell us about your experience of that in practice.
Yes.
At scale.
Yes, this is absolutely an issue. My kind of philosophical stance is, I think, stolen from Tony Hoare, who said something along the lines of, when you're learning how to sail a boat, you kind of have your boat on the sand, and you adjust the sails, and you know how that goes, and you don't take your life vest off when you then take your boat into the water. And that's the spirit with which the contract, so there is no kill switch in the Racket contract system. But we have, but definitely this comes up, and one thing I didn't get to talk about, but is pointed to in that, in the annotated bibliography I mentioned at the beginning, is what we do in Racket is we have something called option contracts, which take ideas from option contracts in the business world. But essentially what it does is it gives the contract programmer the ability to decide whether or not these particular checks need to happen at this particular time. So you program whether or not the contract checking should be happening. So you can, in the spirit of options, I can pass the option to you to check these contracts or not. There's a lot more to say about that one.
So you showed us some contracts that run code and talked a bit about how to blame the contract if something goes wrong with that. But I find the idea of contracts that can do arbitrary stuff, have arbitrary effects, alarming. What your contract might do I/O, it might write to the file system. You're smiling. Doesn't alarm you?
No. I mean, in some sense, you know, I certainly understand what you're saying and why you're coming from and why you raised this point. But I think that we saw this DC contract. It calls unknown code, right? And that's why the projection model is not a good model for contracts, because being able to call into that unknown code to be able to explore its behavior is important and would be ruled out by something that didn't allow those kinds of effects. So, you know, there was a little debate before I added that contract, precisely because it changes the timing of some calls and therefore could introduce errors in principle. And it didn't, however, and it was a very important contract for being able for us. So basically, the bottom line is, I think that yes, that's something we should worry about, but it's something that is our job to find a solution for and not something to outlaw, because it does lead to important invariants that will be checked that will make software better. Thanks.
Okay, so first of all, that was pretty cool. I'd never really seen much of an exposition of contracts that made sense to me. That was useful. The question that I had is, anyway, so it seems like from your methodology, you sort of like, you prefer a contract which can assign blame earlier and more accurately, right?
Sure.
Okay. And so from that perspective, like my first thought was, okay, well then we should use types. But then you showed the effectful contracts, the ones that were using randomness, or we even discussed that it might be useful to have like a contract that does some like, you know, assignment or whatever. And I guess what I'm wondering is why we can't just do that with types anyway. Because we have, it's like these type provider things that people are playing with now. And so for instance, we could seed the type checking of a program with like a random state, right? And so I sort of wonder why we couldn't just try like, so every time we type check, generate some random state and see if our proofs no longer hold.
In some sense, you're just validating essentially everything I've said in this talk, because contracts, I believe, give us a way to know what we should be trying to prove. And that's an important role that contracts should play, and so I'm glad to see that you're getting some value out of that.
Thank you.
I don't have a question. I have an appreciation.
Okay.
I really enjoyed that talk, and one of the things I really enjoyed in it were all the photographs. And some people here will be young enough familiar with the community, so I just wanted to point out something some people might not have noticed. Most of those people are not your colleagues at your university. Many of them are colleagues around the world who also work on the Racket team, and that's amazing. But also a couple of those people, like Michael Greenberg, whose paper I think was co-authored with Benjamin Pearce and Stephanie Wyrick, who are also in the room. That's not the Racket group at all. Amal is not the Racket group at all. And the impact that this has had across the community with ideas moving back and forth, I think has been really important. And we do get that various times, other times, but this is an example of exactly what our community should be doing. I just want to applaud that.
I believe we have time for about 2 more, if anyone has. All right.
Takayuki Marushi from Weekend. I really don't understand that these contracts are different from types, different from tests, because you get to blame where the bug is coming from. So you would like to infect the world with this contract, right?
Yes.
I agree with you. I would like to know how this blaming system is implemented, the implemented cost. And can you infect, for example, language Python with this, or language C with this?
Yes. There's clearly work to be done here.
Yes.
I think that the ideas from Racket do port in a pretty straightforward way to strict languages. And there are small libraries that haven't really taken off in both Python and C for contract systems. And that would be great. That would be great to see more of.
Let me put it in this more concrete way. Suppose there is a function, C function, that takes a float as an argument. Do we have to modify this argument to have the contract in C? No.
No.
Oh, thank you.
We can talk more. And
Let's talk then.
yeah.
Okay. So I have a question about sort of the opposite of gradual typing. Because with gradual typing, you say, well, let's start off with dynamic checks, pairs, contracts, and then like gradually remove them to leave a typed program. But often the checks you want to do are not type-based. Like for instance, maybe you only want to send an email during business hours, and that's inherently a dynamically checked property. So, have you given any thought to maybe using types to check that your contracts are in the right places? So I guess it didn't pick up. So the idea is that gradual typing says let's gradually remove the dynamic checks, but some checks are inherently dynamic, like sending emails through business hours. Have you looked at using types to check that your contracts are in the right place, so that it'll warn you that you're not checking, you don't have a contract where you should have one?
I'm not sure. Okay, I'm stumped briefly, mostly, I think. Fundamentally, contracts are specifications, and really what a contract system is saying is your program and your specification don't agree. So I can imagine that there could be some internal consistency, like we saw some constraints on your specifications that say that they're bogus somehow, and you might use types to eliminate those kinds of things in the same way you eliminate errors from programs in general. But beyond that, I don't know. Sounds intriguing.
Okay. Johan Jeuring, Utrecht University. So I have a question about notation. In the dependent contract, you seemed to have to explicitly pass on the dependencies for the arguments. And you passed on you mentioned the P in the X and the Y. So Ralf Hietze and Anders Leu and I, we wrote a contract library a while ago where we introduced a name and then could use that name in the rest of the contract. So why didn't you use a similar style? It looked a bit strange to have to pass on the dependencies to the arguments.
So the contract combinator makes you explicitly say which arguments depend on which other arguments, mostly because it's cheaper to check the ones that don't have dependency. And so if you explicitly say which ones you intend not to have dependency, it actually changes the timing of the evaluation of those sub-expressions a little bit. So if you have a dependency, even an empty dependency, then the contract system won't try to find out what the contract is until the function is called. And that's less efficient. So that's basically why I put it in.
The efficiency thing.
Yeah.
So you could use it for normal functions as well.
Yes. So if you just don't have if you just don't mention dependencies, then it's the same. That's right.
I believe we're out of time. So thank you.